Welcome to lecture 36. So we are studying about applications of Fourier representation. We are about to end this chapter conceptually, and we have a lot of problems to be solved at. So in this session, we are covering a few problems on what we discussed in the previous session regarding convolution of mixed signals, as well as we will look into the multiplication of the mixed signals in the time domain. Followed by, we have a very important topic called sampling and aliasing. We also call it as, there is one more topic called reconstructions. So with this, we are starting with this session. Let me share my screen. In lecture 36, the topics to be covered are convolution and multiplication. Convolution concepts we have already gone through in the previous session. We are covering up the concepts related to multiplication, and then the important topic called sampling and aliasing. So also there is a topic called reconstruction of sampled signal. So these are the topics left in this chapter, followed by some numerical examples of problems to be solved. So to just summarize the previous session, this is what we studied about the convolution of periodic and non-periodic signal. So y of t is equal to x of t convolved with h of t in time domain. If you take its Fourier transform, it will get in the frequency domain, it will be a multiplication operation, capital X of j omega into h of j omega. So here x of t is a periodic signal, and we are representing it in terms of Fourier transforms by using the relation between ft and fs. The relation between ft and fs has been shown here. This is a relation between ft and fs. You have ft coefficient here, you have fs coefficient here, and we could just substitute the values like x of j omega in the multiplication that we are taking here. So in place of x of j omega, I'm substituting whole of this equation here, multiplied by h of j omega. And here you can see that there is a shifted impulses. So hence we can write it as well as, so x of j omega, because this delta of omega minus k omega naught will be 1 only when omega value is k omega naught. So when omega value is k omega naught, only then this value exists. So that's why I replace this omega with k omega naught, and I write it in this fashion. Summation h of j k omega naught x of k as it is. So this is the convolution property. This is. So we had discussed it in the previous class, and we had a graphical explanation also taken in the previous class. So this is x of j omega. When it is multiplied by h of j omega impulse response, you are getting the output y of j omega. Convolution is happening in the frequency domain, but in frequency domain it is just a multiplication. Okay, and here you can see that it is acting like a low pass filter. Low frequency components are enhanced, whereas high frequency components are suppressed. So this is what we studied in the previous session, and we just want to take a problem numericals on the similar ground. So this problems to be solved with a concept using the previous concept, that is convolution. The question goes like this. Let the input signal applied to an LTI system with impulse response h of t is equal to sine pi t divided by pi t, or 1 by pi t into sine pi t, be the periodic square wave depicted in figure 4.4. This is figure 4.4. Use the convolution property to find out the output of the system. So this is a question. Okay, so the solution goes like this. So very first thing is, first h of t is given here. Okay, so x of t and h of t, both of things are very important for us because we have been asked to find out y of t. Y of t is nothing but x of t convolved with h of t, right? So here the h of t, the frequency component or frequency response of h of t can be written as if I want to write its ft pair, it looks like this, capital H of j omega. Now h of t is given as sine pi t divided by pi t. So you know that it can be converted in terms of a sinc function, right? So it's almost it is resembling a sinc function. Whenever you have a sinc function on one of the domain, on the other domain you will be having a rectangular pulse. This is what we have studied. So on the other side, it is understood that we will be having a rectangular pulse. H of j omega is equal to 1 for omega less than or equal to whatever I'm having here other than t, pi. 0 for omega greater than pi. This is a rectangular pulse we have. This is about h of t. Now regarding x of t. So what is the information given for x of t? So here x of t's information is a figure 4.4, that is the rectangular pulse. And I write x of t in terms of equation, mathematical equation as 1 for, minus t naught till t naught. So here minus t naught is 1 actually. So minus 1 to 1, I'm writing it in general. So let me write t naught as 1. Okay. So 0 rest everywhere for t greater than t naught within that period. So this is the information regarding h of t and x of t that we are having. Now h of t's frequency component or response, we have written it here. Now similarly for x of t, if I'm supposed to write the frequency representation or Fourier representation, you know that it's a periodic signal. H of t was not a periodic signal, we could apply ft directly, but this is continuous time and a periodic signal. For continuous time and periodic signal, we should have applied fs. So x of t should be applied with fs because it is periodic. So first what I do is I write the ft pair of x of t, fs pair with respect to omega naught. You will get it as x of k. Now what is x of t given here? It is a square waveform and it has been mathematically written as uh, so- mm, sorry, minus t naught. One second. So it is written as, from the previous slide, this is how it is written. So in place of t naught, it is 1. Okay. I'm just trying to generalize the things because when you refer back, so these equations are as it is, so that you can link it. So fs omega naught is equal to pi by 2. Okay. So here x of k is equal to 2 into sine k omega naught t naught. It is taken from fs. If you refer the fs coefficient extraction topic in the chapter 3, you will find out same equation, same as it is equation I have taken. Now here I go on substituting 2 into sine k omega naught is pi by 2. Why omega naught? I am taking it as pi by 2 because omega naught is nothing but 2 pi by t. So what is t? T is, you just hear, this is minus t naught, this is plus t naught, this we are writing it as, this is one full period, we are writing it as 4. T is equal to 4. From here to here, t is equal to 4. So hence t is equal to 4, you are getting it as pi by 2. Okay. So omega naught is pi by 2, that's why. So in place of omega naught, I'm writing pi by 2. T naught is 1, we have already analyzed it. So again, t is here, 4 k omega naught means pi by 2. So you get it as sine k pi by 2 divided by k pi. So quickly when you refer, when I give this equation as x of t equal to 1 in this range, you should be able to write this one. Especially for sinc function and rectangular function, I suggest you to by heart it or remember this equation. So we are using ample amount of time. So I mean, very frequently, oftenly these equations. Hence, I want you people to remember this. Next is, let us now relate this Fs. This is Fs, but our intention is to find out Ft. Let us relate Ft and Fs now. So we know the equation as x of j omega 2 pi. This is from the first relation that we derived. K is equal to minus infinity to plus infinity, capital X of k, delta of omega minus k omega naught. So we will directly substitute the value. Summation k is equal to minus infinity to plus infinity. In place of x of k, we have found out that it is sine k pi by 2 divided by k pi. So then delta omega minus k omega naught is nothing but pi by 2. Okay, so here this pi and this pi cancels. You are left with uh, uh, summation k minus infinity to infinity 2 sine k pi by 2 delta of omega minus k pi by 2. So this is ft. So we could find out ft of h of t, that is h of j omega, we got it, and x of j omega also we got it. Now we will find y of j omega. This is what is our intention. See, use the convolution property to find the output of the system. Output of the system is y of t. We need to find out y of t. How do we find out y of t? We first calculate y of j omega and we will take the inverse transform. So y of t, why we are converting it to frequency domain? Because convolution becomes multiplication. It is much simple performing multiplication versus performing convolution. That's why we are doing it. So this is h of j omega into x of j omega. Very simple now. What is h of j omega? H of j omega is written as, I'll write it here. So it is 1 for omega less than pi or equal to pi and 0 for greater amount of time. And what is x of j omega? It is here. It is here. Now, what is the thing that you should decode from it is, see, if I substitute k's value. So if k value is substituted as 0, if k value is substituted as 0, then what we get is, so you have to substitute, uh, such that omega should not exceed the period. It should not exceed the period. Okay, so omega naught here, it is 1 only for the range minus less than or equal to pi. So we should select k's value such that, k's value here such that omega value should not exceed greater than pi. So hence in range, sorry, omega less than pi, so we get only these values. Only three values we get it. So in three values, when you substitute, the h of j omega is 1. Okay, so that's why I take the next slide. So what I write it here is h of j omega is equal to 1 when I substitute k's value as 0 or plus or minus 1. So hence y of j omega I consider for only summation k is equal to minus 1 till plus 1. So I'll just copy down this one. K is equal to minus 1 till plus 1. 2 is there. I'll take the 2 here. 2 sine k pi by 2 divided by k delta omega minus k pi by 2. So this is x of j omega. H of j omega is 1 in this range. It is 1 in this range. Within that range, it is 1. So if I substitute k is equal to minus 2, what happens? If I substitute k is equal to minus 2, what happens? So minus 2 means here 2 cancels, you will get pi. So if you get pi, delta omega plus pi, you get it as. So this delta function will be non-zero only when omega is equal to minus pi. So you are exceeding the limit. So hence I'm not taking, for example, you take the k value as 3. So 3 pi by 2 is greater than, pi. Okay, so if you substitute omega is equal to greater than pi, minus or plus, so it is exceeding that limit where h of j omega goes to 0. Your h of j omega is found out as it will goes to 0 when your omega exceeds pi. So if you multiply it, the result will be 0 anyhow. So hence I am restricting myself that such that your omega should not exceed pi. And such ranges are k is equal to 0 and plus or minus 1. So hence I have taken this. Now, so I write it. First I substitute k is equal to minus 1. What do you get? 2 sine of minus pi by 2 divided by k value is minus 1 delta of omega plus pi by 2 because k is substituted as minus 1. Then plus when you substitute 0. So when you substitute 0 here, sine 0 divided by 0. So 0 by 0 forms, so hence you cannot perform. So you have to perform L'Hospital's rule. If you apply L'Hospital's rule, I don't go in detail because you are already, understood about it. So differentiate the numerator and denominator. If you differentiate the numerator, what you get? I'll write it here as a rough work. Okay. So if you differentiate, you will get it as 2 cos of k pi by 2 into pi by 2 because it is with respect to k, so hence it is 1. So this 2 and this 2 cancels. So now you supply k is equal to 0, cos 0 is equal to 1, 1 into pi is pi. So you are left with pi. So hence I write it as pi. So whole of this term I got it as pi. Now here if I substitute k is equal to 0, you get it as delta of omega. So plus next last one, k is equal to 1 if I substitute 2 sine pi by 2 divided by I had substituted 1 delta of omega minus pi by 2. So therefore the final equation I'll write it as y of j omega is equal to 2 into, so sine minus sine, this minus comes out, minus minus cancels, sine pi by 2 is 1, so delta omega plus pi by 2 plus pi delta omega plus 2 delta omega minus pi by 2. So this is the answer for convolution. I hope there are no doubts. Now very next topic is multiplication. So convolution in time domain is multiplication in frequency domain. Similarly, multiplication in time domain will be convolution in frequency domain. That's what is our next topic. Okay, so it's a duality property, vice versa. Fine. So here I'm taking y of t is equal to multiplication in the time domain, g of t into x of t. So when you take its Fourier transform, y of j omega is equal to 1 by 2 pi g of j omega convolved with h of j omega. This we had studied it in multiplication property of the ft in the first part of this chapter. Okay, same thing, multiplication property. I have extracted here, taken it here. If x of t is periodic, we may apply the multiplication property by employing the ft. If it was non-periodic, this suffice the need, because for non-periodic signal you need to apply ft itself. But for x of t is periodic, we should apply ft only after relating ft to fs. So this is the place where we are doing this process, relate ft to fs. So x of j omega is ft coefficient. This is fs coefficient. This is a relation. So hence, in place of x of j omega, I just write the relation between ft and fs. That's it. Only this change. Rest everything is same. Okay. So this is the change, and you had that 2 pi and this 2 pi cancels. So you get this equation. Next, the shifting property of the impulse function implies that convolution of any function with shifted impulses result in shifted version of original function. For example, here, whenever we get a shifted impulses, we have that scope to truncate the term still more. So what we do is summation k is equal to minus infinity to infinity, capital X of k, take it aside, g j omega delta of omega minus k omega naught. So here I substitute, this delta function exists or non-zero value. It will result in non-zero value when you substitute omega is equal to k omega naught. So when I substitute omega is equal to k omega naught, then only this will be non-zero. Okay, so that's why I substitute omega is equal to k omega naught throughout. So if I do that, so what I get is in place of omega, I substitute omega minus k omega naught. So it will suffice the problem, or this will justify like g into j omega, g of j omega into delta of omega minus k omega naught can be written in this way. Okay, so this way is same as writing this way. So this is the multiplication property of periodic and non-periodic signal. So using this, we shall solve the very next problem. So before we go to the next problem, we have the representation of frequency coefficient. If g of j omega's frequency coefficient spectrum is in this way, and if x of j omega's signal is this way, you know that we are convolving. We are not multiplying. We are convolving in the frequency domain. So convolution in the frequency domain is not as simple as you do the multiplication. So you can just check. So this spectrum is just replicating wherever you have coefficient of x of j omega. So here it is, here it is, here same thing, here it is, here it is. So it goes on extending. So convolution in frequency domain is again complicated. Okay, convolution in frequency domain becomes multiplication, but multiplication in time domain becomes convolution in frequency domain. So convolution in frequency domain, this is how it takes place. Okay, so but it is a multiplication in the time domain, simple multiplication in the time domain. So we shall take one problem so that your understanding gets better. Consider a system with the output y of t is equal to g of t into x of t. Let x of t be the square wave depicted in figure 4. Same 4.4 figure I have taken. Find y of j omega in terms of j omega. So this is generalized answer they have asked. Then they have made it specific. What they have asked us, you have to find out y of j omega if g of t is cos t by 2. So for this, the solution goes like this. Solution. So very first thing, I'll be pretty straight forward here because already have been explaining the same concepts repeatedly. The square wave has fs representation as, so your x of t is given as this one. Its fs we have already taken in the previous problem itself. We have already taken omega naught is equal to pi by 2. Why pi by 2? Because t is equal to 4. T is equal to 4. Omega naught is equal to 2 pi by 4. So that's why pi by 2. Okay. So this we have already taken here. I'll show it. Here, this one. X of t, if it is this one, x of k sine k pi by 2 divided by k pi. So hence I write it as sine k pi by 2 divided by pi k or k pi. Okay. So now what we do is I use the equation previously derived, that is this equation. I use this equation. So this equation states that so y of t is equal to g of t x of t. If it is multiplied in the time domain, so when I take its ft, so we have derived it as k is equal to minus summation k is equal to minus infinity to plus infinity x of k g, capital G, j of omega minus k omega not double bracket. So this is a relation we have extracted from the previous relation. Okay, so now I substitute x of k from whatever we have just now derived. This is x of k. So this y of j omega is equal to summation k is equal to minus infinity till plus infinity. In place of x of k, I write it as sine k pi by 2 divided by pi k g of j of omega minus k. Omega naught means pi by 2. So this is the answer. This is the answer for the first question, first part of the question, this one. Now second part, I have to substitute a g of t is equal to cos t by 2. Now we know that if g of t is equal to cos t by 2, if I take its ft, I'll directly take its ft. You know, it's a periodic signal, I know. We have to apply fs, but we have already found out ft of a cos signal in the very first relation. So I use the relation between ft and fs, and then directly I write g of j omega as pi delta omega minus omega naught in place of omega naught, or not omega naught. So here, if it is cos omega t, omega we were writing it here, right? Omega naught we are writing it here. Here it is 1 by 2, hence I write as 1 by 2 plus again pi delta of omega plus 1 by 2. That's it. So that's it. So thus y of j omega is equal to, I copy from the previous slide the equation that we derived, this equation, k is equal to minus infinity till plus infinity sine k pi by 2 divided by k delta of omega minus 1 by 2. Okay, this is 1 by 2, omega minus 1 by 2, but you know that it is g of j omega minus k pi by 2. So omega is nothing but, it should be, omega should be replaced with, so we have omega is replaced with omega minus k pi by 2. This additional term will also be there, that also we should write. Then plus, so here bracket has been placed, pi, one second, delta omega plus 1 by 2 minus k pi by 2. One second. So here this pi and the pi which was coming from here, these two get cancels. So I'll write that pi here, this get cancels. So this is the final answer. This is a final answer. And to sketch it, to sketch this wave, yeah, to sketch this waveform, I just take some important points here. Rest you can ignore. So here, when k is equal to 0, sorry, when omega is equal to 0, when omega is equal to 0, so omega is equal to 0, what we are supposed to do is, initially I take k is equal to 0. So when I substitute k is equal to 0, 0 by 0 form, you know that differentiation should be taken. So you get it as cos k pi by 2 into pi by 2. So here it gets differentiated. So you got something called pi by 2 out here. And when k is substituted as 0, this goes off, this goes off. You are left with delta of omega minus 1 by 2, omega plus 1 by 2. Okay, so this delta will exist only when omega is equal to 1 by 2. So delta omega is 0 at omega is equal to 0. Hence you have 0 here. So it will have the value only when your omega is substituted with 1 by 2. So if I substitute 1 by 2, what do you get? 1 by 2 minus 1 by 2. Anyway, k is made 0. 1 by 2 minus 1 by 2. So it goes to 0. Delta of 0 is 1. So here pi by 2 has come. Pi by 2 is a signal. Same thing when you substitute omega is equal to minus in terms of here. When you substitute omega is equal to minus 1 by 2, also you get the same thing. Similarly, you can find out the rest of the values either within the range pi by 2. Pi by 2 here, pi by 2 here. Rest everywhere it goes on, changing. So this is a problem related to your multiplication. Okay, so actually it is a multiplication with a square wave. The very next topic, and almost the last topic I can say of this chapter, of this unit, is sampling, aliasing and reconstruction of the signal. So sampling is a very important concept and it acts as a prerequisite of most of your future semester subjects. Okay, so sampling, we have been learning with the this about the sampling from very first chapter. I had taken this word called sampling. So what is the meaning of sampling? So sampling is, think that I try to make it very simple. Think that give you a task to just record a temperature of a day at every 4 hours. So when you record a temperature of a day at every 4 hours, you may note that in the initial morning it will be cold, in the noon it is a bit hot. Again, it goes on reducing as evening approaches, it will be still more less. But there might be a chance that when I ask you to submit the report, you will submit that okay, day was pretty normal. So as it was at 12 noon, it was increasing, and after that it was falling, the falling of the temperature. You might record like that. But there might be chance that within that 4 hours of sample amount of time, the time you were taking, the temperature you were recording at every 4 hours. So within that next 4 hour, there might be a chance that suddenly there was a rain, because of which temperature has might have come down. You might have failed to record it because I had given you a task to record the temperature at every 4 hours only. So that change of the behavior in the temperature you might have failed to record. Okay, so that we says that that sampling has not been appropriate to record the changes appropriately. So next, for the next batch of the students, what I do is to maintain the accuracy, I ask them to record the temperature every hour. I do know that in one single hour, from this hour to next hour, there is less possibility of drastic change in the temperature. There might be sometimes, but it is less possibility. Hence, my records of the temperature will be much more appropriate when my sampling time is 1 hour. Now, there might be some introduction of mm, uh, um, wrong answers, or some introduction of errors there, but I want to reduce the sampling time still more in order to be very accurate. What I do is I ask the next batch of the students to record the temperature every minute. Now there is no chances of going wrong. There is not at all a chance of going wrong, but every minute to record a temperature, it is huge. It takes lot of efforts from a person, right? That is how the sampling goes in signals and system also. If you try to be more accurate, you should end up recording more number of samples in the by reducing your sampling rate, by increasing sampling rate, or else by reducing the TS, sampling period. If you just take samples at too much delay, then there is you will end up in you know a lot of errors in the sampling. So that's why sampling plays a very important role. So here we go on with the understanding of the sampling technically. A sampling operation generates a discrete time signal from continuous time signals. You remember that. Temperature is a continuously varying phenomenon, but we are recording the temperature at every 1 hour or at every 1 minute, right? So it means at every 1 minute you got some value. We call it as discrete time, right? So you are recording a temperature at every 1 hour. So total 24 hours, 24 different values you have. It is called a discrete time signal. But temperature actually it is varying at every second also. Your temperature thermometer might be not that much sensitive to record it, but it is a continuous phenomenon. So from continuous time signal, we could record digital discrete time signal. This process itself is called as sampling operation. So whenever you hear the sampling operation very next time, whenever you hear, you remember this temperature example. So this will be helpful for you to remember the sampling operation in a easier way. Sampling of continuous time signal is often performed in order to manipulate the signal on a computer. So if you want to feed some data into the computer, I need some finite values. In order to make a finite values, I have to break the continuous time signal into lot of discrete components, single components, so that I can store it in my device and process it. So that's why sampling plays a very important role. Sampling is also performed to change the effective data rate, an operation termed as a subsampling. We will just come with more explanation on subsampling in the very next slides. So mathematical representation of the sampling as a product of given time and impulse train is given like this. So this is a result of the sampling, like recording your temperature at every TS amount of time. That's what is done here. So think that this is a temperature variation for a day. This is a temperature variation per day. This is time. Okay, so it is get just varying according to the you have recorded up till now, it is a future occurrence. So you have recorded your temperature is going on, and you are supposed to extract the sample like this, in this way. Okay, so for that what I do is For this x of t signal, I multiply impulse train. This impulse train is designed such that delta function occurs at every ts amount of time. Ts, 1 ts, 2 ts, 3 ts, it goes on. It goes on. Okay, this is when this goes on, so it means this gets multiplied with a continuous time signal. So wherever it is multiplying with amplitude 1, the signal will be retained. Wherever it is multiplied with 0, that signal will be lost. So hence you will end up getting this signal. Just end up in getting this signal. This signal x delta of t is a sampled signal. This is the original signal. This is impulse train that I'm using for generating sample signal. Impulse train is found out by summation shifted impulses of delta function. So delta function shifting property, using shifting property we could design this impulse train. So when I multiply it with a continuous time domain signal, so you get it the sampling signal. So the same phenomenon, graphical thing, what I have shown, we will represent it using the equation now. So using equation, the very first thing I'm writing is x delta of t. So what is x delta of t? X delta of t is a sampled signal. Okay, so it's a sampled signal. So when it is sampled signal, it is a summation. I can write this x delta of t as, x of n, delta of t minus nts. Delta of t minus nts means, see, initially think that n is equal to 0. So you have only delta of t. So delta of t into x of 1 means delta of t exists only for, so when n is equal to 0, your answer is x of n delta of t, because n is equal to 0. So you get only this. So delta of t exists only for t is equal to 0. Hence it is x of 0. First sample. I took the first sample. Or how to extract the second sample? N is equal to 1. X of n delta of t minus n is 1 ts. 1 ts means delta function exists when t is equal to 1 ts. When t is equal to 1 ts, 1 ts minus 1 ts goes to 0. Delta of 0 is 1. So x of 1 ts means this particular signal will be extracted here. Similarly, n is equal to 2, you get x of 2 ts. So when I add all these things, I call it as summation. That's why I write it in this fashion. Summation x of n delta of t minus n ts. Please understand the mathematical model trying to relate it with graphics or the graphs. Then only you can understand, you can relate, you can apply the mathematics. Okay, so you understood what is x delta of t, why it is represented in the given form. So now we use nts, x of nts for x of n. It is means same. So I have shown it here. X of n, it is nothing but x of 1 ts when n is equal to 1. So if n is equal to nts, okay, if I write it as nts, here it is 2 ts, 3 ts, like that I can write it as nts. So that is what is written here, nts. So we use x of nts for x of n. It is same, as good as same. I have shown it in the previous slide. That's why I'm writing it in this manner. So here, since x of t delta of t minus nts is equal to x of nts delta of t minus nts. Why? Because, see, this delta function exists only when t is equal to nts. When t is equal to nts, replace t everywhere with nts. Nts here, nts here. Nts minus nts goes to 0. Delta of 0 is 1. 1 into this one, x of nts. So that's why you can write in this fashion. We may write x delta of t as product of time functions. So this is very important. What I'm trying to represent this x delta of t in the graph that I have shown. Very first graph. This one. I want to represent in this form. X of t into p of t is nothing but x delta of t. So that graph thing I had shown, that I want to write. X of t is the given signal, is a continuous signal, that temperature phenomenon, continuous time signal that you imagine here. So p of t is an impulse train. So when I multiply these two things, I'll get a sampled signal. That is what has been written here. Okay, so but P of t is represented as summation shifted, sum of shifted impulses. That's a meaning of impulse train. Summation n is equal to minus infinity to plus infinity delta of t minus nts. Okay, so now if I want to perform the operation, multiplication in time domain becomes convolution in frequency domain, that we are already aware. Okay, in the very previous topic we have understood this 1 by 2 pi x of j omega delta, I mean convolved with p of j omega. So I have taken the same values for the reference. P of j omega is nothing but, you know, we have computed the Fourier transform of the impulse train in the very first topic of relation between ft and fs. So if I take its Fourier transform, we were getting again impulse train itself with 2 pi by ts summation delta of omega minus k omega s. So 1 by 2 pi as it is, 1 by 2 pi as it is, x of j omega as it is. So convolved with 2 pi by ts summation delta of omega minus k omega s. Now, further simplification will result in 2 pi cancels, 1 by ts taken outside, summation, you know, so this x of j omega convolved with shifted impulses. Whenever there is a shifted impulses, you can just as well write like how we did for g of j omega in previous multiplication property. In the similarly, omega you will be replaced with omega minus k omega s. So this is the sampled, signals Fourier representation or Fourier transform in the frequency domain. Okay, so this is about the sampling process. Now, graphically we shall understand. So, in general, we write the spectrum. We call it as spectrum. Spectrum of a continuous time signal. Normally, spectrum of a continuous time signal will look like this one. So, this is a frequency component varying from minus W to plus W. So various frequency components are there, and frequency components are accumulated towards the origin. This is how we normally represent the frequency spectrum. Same looking kind of the diagram you will observe in the subjects related to communications in your next semester. So this is a spectrum of a continuous time signal, frequency spectrum. We call it as a frequency spectrum of a continuous time signal. Okay, so when I sample it, spectrum of sampled signal when omega s is equal to 3 omega 3w. So when I sample it with some frequency sampling rate as omega s is equal to 3 capital W, it would look like so omega s, it is here, minus omega s is here. This spectrum will be replicated at every omega s, 1 omega s, 2 omega s, 3 omega s, like as k varies, it goes on replicating. These are replicas or harmonics of the frequency components. So x delta of j omega will result in this fashion. Actually, continuous time spectrum should have been look like this, but the sampled signals frequency spectrum will look in this fashion. Similarly, I take few more examples. If omega s is equal to 2w, if it is 2w, you can see somewhat a bit of, almost touching. This spectrums are almost touching, not overlapping. Now when I increase, or when I just increase the frequency, or you decrease the frequency here 1.5 w, so here you can see that there is an overlap. When there is a overlap, it is loss of information. So you should avoid overlapping so that there is no loss of information. So here you can see that this is decreasing and it is increasing the same rate. Decreasing and increasing the same rate will result in some constant value like this. The signal would look like in this way. Hence, you should be very careful in choosing this omega s. How to choose this omega s? There is some understanding for that, so that we will understand now. So why it is very important? Why these things signals are very important? If you get the spectrum in this manner, it is easy to reconstruct. No information is lost. If you get the signal like this, you can marginally reconstruct properly. But if you get the spectrum in this fashion, you will lose lot of informations. So some frequency components are overlapping. You are missing these frequency components. These frequency components are missing from your information. So hence when you reconstruct, some signal will be lost. So hence reconstructions system should be designed such that it should you know result in very accurate answers at the output. For example, if I'm speaking now, you are listening almost accurate things, accurate words at your end. It's because the reconstruction system is so accurate. So how to do it? Here it shows. See, if this is the continuous time signal, the thick bold line is a continuous time signal. The discrete time signal is shown in the vertical bars here. And when I join it, so the reconstructed signal is dotted lines. Dotted curve is a reconstructed signal. So if I'm whatever I'm speaking in real, if it looks in this fashion, okay, we will take its samples at my end in my laptop. It will process it, it will transmit it, and you will receive it. And when your receiver decode it, and when you listen it, it might look in this fashion. It might look in this fashion. Of course, it is more accurate than what I'm showing, but it might look in this fashion. So x1 of t is dashed line, x2 of t is a solid line that we have some set of samples. Okay, so the smoothness or rate at which the time domain signal changes is directly related to the maximum frequency that is present in the signal. So frequency, if it is very high, smoothness or rate at which the time domain signal changes, it changes. So if it is more smooth, the frequency present will be maximum frequency present will be comparatively less. Hence, constraining smoothness in the time domain signal corresponds to limiting the bandwidth of the signal. So these terms we'll understand in the coming slides. Sampling theorem, very important. Please listen carefully, very important. Sampling theorem. X of t and is ft pair is given here. Represent a band limited signal. It is a limit some signal. So that x of j omega is equal to 0 for omega greater than omega m. If omega s is greater than 2 omega m, where omega s is 2 pi by ts, we know that omega s is 2 pi by ts, is the sampling frequency, then x of t is uniquely determined by its samples, x and ts. So very complicated to understand at the first sight, but I'll make it much more simpler. Let me complete the explanation. The minimum sampling frequency 2 omega m is termed as Nyquist sampling rate or Nyquist rate. The actual sampling frequency omega s is commonly referred to as Nyquist frequency. Remember, if Fm is equal to omega m divided by 2 pi is the highest frequency present in the signal, and Fs denotes the sampling frequency both expressed in hertz, then sampling theorem states that Fs should be greater than 2 Fm, where Fs is 1 by Ts. Alternatively, we can also write it as Ts less than 1 by 2 Fm to satisfy the conditions of the theorem. So Nyquist sampling rate or Nyquist rate is nothing but the minimum sampling frequency, okay, 2 omega m, and Nyquist frequency is the actual sampling frequency. Now I have read out just as it is. Now I'll come to the explanation. So another 5 minutes, I want your full concentration. So think that I'm having some signal like this. Some signal like this. It will be having a lot of frequency components. Frequency is determined by how much rapidly it is changing its value. So more rapidly it is changing its value. I'll continue it. Okay, think that the signal is like this. Here it is less rapidly it is varying. Here very less rapidly it is varying. Here drastic variation you can see. Drastic variation. Right? So where there is a very drastic variation, there you will find the highest frequency, maximum frequency. So when there is maximum frequency, normally we represent it in terms of omega m, angular frequency. So this maximum frequency is very important for me. Why? Because in order to represent this signal, in order to extract the proper samples out of the signal, I have to take samples such that I have to record its peak as well as its crest. Peak and low properly. When I can record it? When my sampling rate is much more rapidly than this maximum frequency. My sampling rate should be much more faster than this maximum frequency. It should fetch 2 samples in this frequency, in this component itself. Then only I can say that I can record this variation. To record this sudden variation, my sampling time should be much more faster than this. I hope you're understanding. Hence, what Nyquist, the scientist called Nyquist, did is he defined a sampling theorem. What he said is, to record the samples of the rapidly varying signal, you have to follow one simple rule. What is that rule? Is your sampling frequency should be greater than greater than 2 times of maximum frequency. This is the maximum frequency. If I take my sampling double the rate, for example, it is suddenly changing, I'll record two more datas, two data still in this suddenly varying, rapidly changing signal. That is quite okay for me. That's good. We have taken the samples of every variation. That's a meaning. This is a maximum rapidly varying. I'm taking two samples out of it. That's sufficient. So this will suffice the problem that we can extract every samples from the signal. So this is defined by the Nyquist. Hence we call it as Nyquist criteria. And you know that omega is related as 2 pi f, which is nothing but 2 pi by d. Okay, if it is omega s, we write it as 2 pi fs is equal to 2 pi by ts. So in whatever form you have been asked, you have to represent it. Okay, for example, omega s and fs, if I want to relate, I write it as fs is equal to omega s by 2 pi. That's it. Here it is. And if I want to relate these two things, fs and ts, what I do? 2 pi and 2 pi cancels. Ts or fs is equal to 1 by ts, or ts is equal to 1 by fs. That is here. And you know, omega is greater than 2 omega m. So if I write it as 2 pi fs, 2 pi fs greater than 2 into 2 pi fm. 2 pi and 2 pi cancels. Fs is greater than 2 fm. That is what is here. Okay, so everything is telling that your sampling frequency should be higher or greater than 2 times the maximum frequency. That's it. That's it about the sampling. So remember this explanation. So it will be very much useful in your future things. So examples related to sampling we will take up in the next session. So with this, we are concluding today's session. Thank you.